Hi, my name is Ciara Garrison, and I'm going to be showing how to do video problem number 2 today.
Problem number 2 asks us, water is pumped from the large tank shown in diagram A. The entrance to the pipe section is sharp-edged and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications and is shown in diagram B. Part A asks us to determine the volumetric flow rate for this system. And doing that, we will start by calculating the friction E over D, which is going to be, or looking at what we know from the problem, having it be sharp edged, the KL value is going to be 0.5. Dealing with a cast iron pipe, the roughness value E is going to be 0.26 millimeters, which will go to 0.00026 meters. The length is 2 meters. There's a fully turbulent flow observed, and head rise is going to be 20 minus 2,000 Q squared. So plugging in E over D, we're going to get 0.00026 meters over 0.07 meters, which is going to give us 0.0037. And looking at the Moody diagram, we'll learn that at that value, the friction factor is 0.027, and the Reynolds number is going to be observed to be about 3.9 times 10 to the 6th. And moving on, we will plug those values in, that value, into our head loss equations. For starting with major, it's going to be friction factor times L squared over 2G, which equals 0.027 times 2.0 meters over 0.07 meters. And we're also going to know that velocity equals Q over A, and our area is going to be at the exit region 0.2 versus 0.1. So it's going to be area 2 equals pi over 4 times 0.07 squared, which is going to be 3.8 times 10 to the negative 3 meters squared. And that squared, which we're going to need, is going to be 1.38 times 10 to the negative 5 meters to the 4th. And then plugging that in up here for our V squared, we're going to do Q squared over 3.8 times 10 to the negative 3 squared, which is going to be that, over 2 times 9.81. So then we get that our major head loss is going to be 2850.06 Q squared. Now looking at our minor head loss, which is going to be KL times V squared over 2G, and KL is known to be 0.5 because of the sharp-edged pipe. V squared is going to be Q squared over 1.38 times 10 to the negative 5 over 2 times 9.81, which is then equal to 1847.06 Q squared, and our total head loss is going to be 4697.12 Q squared. And we're then gonna plug that into Bernoulli's equation, which is obviously P1 over gamma over V1 squared, or times plus V1 squared over 2G plus Z1 plus head rise is equal to P squared, P2 over gamma plus V2 squared over 2G plus Z2 plus head loss. And we're going to know that because it's at atmospheric pressure, P2 is going to be equal to 0, as well as P1. So this will go to 0, this will go to 0. And the V1 is equal to 0 as well, so this will go to 0. We know that if this is set up like this, with Z1 minus Z2 plus HP, P2 gamma plus V2 squared over 2G plus head loss, Z1 minus Z2 is equal to 6 meters right here, which is going to give us these going to 0. We're going to get 0 plus 0 plus 6 plus 20 plus minus 20 minus 2000 Q squared equals 0 plus Q squared over A squared, which is going to be 1.38 times 10 to the negative 5, all over 2 times 9.81, plus the head losses, which is going to be 4697.12 Q squared. Now solving for that Q squared value, we'll get 26 over 10,391.55 is equal to Q squared. So then we can find that Q flow rate is equal to 0.05002 meters cubed per second, which is our answer to part A. And then we'll move on to part B, which is asking us, we know that the Reynolds number for a fully turbulent flow is going to be greater than 3 times 10 to the 6th. Our Reynolds number is 3 times 3.9 times 10 to the 6th, which is greater than 3 times 10 to the 6th, proving that the flow is in fact fully turbulent, which brings us to part C, asking us if the pump is 70% efficient, determine how much power must be supplied to the pump. So we're going to look at our efficiency equation, which is fluid density shaft. We also know that the work of the shaft can be, or the pump can be solved as total head losses, which, plugging in our values, we can find, knowing that the fluid density of water is 1 as well, gravity is 9.81. We know our flow rate now to be 0.05, and our total head losses, once we plug in Q in our total head loss equation, we end up with 11.75, giving us the work is equal to 4.04 pump. Thank you for watching.